Hello, this video is about inverses of matrices. So in the previous videos, we talked about matrix multiplication. We also talked about addition of matrices. So you can add two matrices if they're the same size. You can subtract two matrices if they're the same size. You can multiply two matrices, not necessarily if they're the same size, but if you have an m by n matrix and an n by p matrix, you can multiply those. But the order in which you multiply them matters. Remember, the number of columns in the first matrix has to be equal to the number of rows in the second matrix. In that case, the matrix multiplication is defined. But you can't divide by a matrix. The closest thing you can do is to multiply by the inverse of a matrix if it exists. And that's what we're going to talk about in this video. Well, we actually already sort of introduced this concept in the topic of invertible linear transformations. So remember that if you have a linear transformation from Rn to Rn, a linear transformation T from Rn to Rn is said to be invertible if it is one-to-one and onto. Let's just recall what the words one-to-one and onto mean. So one-to-one means that you can't, it means that whenever you have two different inputs, you get two different outputs. That's basically what one-to-one means. And one way to check when you have a linear transformation is to look at all the vectors that go to the zero vector. If that set is only the zero vector, if only the zero vector goes to the zero vector, then T is a one-to-one linear transformation. Onto means, so if you think of this first Rn is the domain, the second Rn is the codomain or target. If you look at the collection of outputs, so if you imagine plugging in every single vector in Rn into your function T and looking at the outputs, if you get the entire codomain Rn, that function T is called onto. And one way to tell if a linear transformation is onto from its standard matrix, do you remember what the standard matrix is? If I have a linear transformation T, what is the definition of the standard matrix? It's the matrix where I take the first column to be T of E1, the second column is T of E2, and so on. That matrix is called the standard matrix of T. And if I have the standard matrix of T, how can I tell if T is onto or not? If when I row reduce the matrix, I get that matrix A, the standard matrix, I get the echelon form of it. And what do I look for? If there's a pivot in every row. Because if there's a pivot in every row, remember what that means? It means that whenever I have AX equals B, no matter what B is, AX equals B has a solution, has at least one solution, and that's a way of phrasing that T is onto. That T hits every possible B, every possible output B is obtained by some input. Okay, and if you have a function T that's one-to-one and onto, it has an inverse. Okay. So here's my picture. Okay, let's say that you have something like R2 and then R2. If you have an invertible matrix, if you have an invertible linear transformation, what will happen is that E1 and E2 will go to linearly independent vectors like this. Like maybe that's T of E1. Who knows? Maybe that's T of E2. The point is that these are linearly independent. And they will span R2. The linear independence guarantees that T is 1-to-1. And the fact that the columns of A, which is T of E1, T of E2, span R2, that's the same as saying that T is onto. But we've seen that whenever you have a linear transformation T from Rn to Rn, so it's the same n, if it's 1-to-1, it's automatically onto. So one way to think of invertible is just, it's a linear transformation from Rn to Rn that's 1-to-1. Or a linear transformation from Rn to Rn that's onto. Because if in the case when you have a linear transformation from Rn to Rn, 1-to-1 will imply onto, and onto implies 1-to-1. And the reason for that was because if we recall that T being 1-to-1 is the same as saying that A has a pivot in every column. And if you have a pivot in every column and A is a square matrix, then you have to have a pivot in every row. I mean, if you have a n by n matrix, if you have a pivot in every column, well, there's n columns, right? So you have n pivots, and you have n rows, so you have to have a pivot in every row. So A has a pivot in every row, and that's the same as T is onto. So this is if T is a linear transformation from Rn to Rn. If the linear transformation T maps from Rn to Rn, not from R2 to R3, not from R3 to R2, it's from R2 to R2, R3 to R3, etc. Because otherwise, this equivalence will not be true, right? I mean, if you have a different number of rows and columns, then if you have a pivot in every column, you might not have a pivot in every row, and vice versa. Okay, so in this case, we say that T is invertible. And we call the standard matrix an invertible matrix, and call A an invertible matrix. And in general, we say that a matrix, we say that the square matrix A, remember you have, whenever you have a matrix, you get a linear transformation from Rn to Rn, M. If you have a square matrix, it's invertible if the linear transformation that maps the vector x to the vector ax is invertible. And so that's the definition of invertible, so please memorize this. Now I should say that some textbooks define invertible matrices in a different way in terms of matrix multiplication, and we'll see that it's actually equivalent. So we're talking about the same type of matrices. And let's just recall that what happens when you take the reduced row echelon form of an invertible matrix, what do you get? You get the n by n identity matrix, because you have a pivot in every row in column. So when you kind of sweep down, everything below it turns to zeros. When you sweep up, when you're doing the row operations to clear the entries above the pivots, you get 0. And then to get in reduced row echelon form, well, the pivots have to be 1, and so you just get the n by n identity matrix. And vice versa. If the reduced row echelon form is the identity matrix, you have a pivot in every row and column, so the matrix is invertible. Okay. Okay, so we already can see if you're given a matrix, how to tell if it's invertible or not, right? Find the reduced row echelon form. If you get the identity matrix, the matrix is invertible, otherwise it's not invertible. Let's think of different ways of describing invertible matrices. Most square matrices will be invertible. So it's an important class of matrices. Well, we know that if you have an invertible linear transformation T, then it'll have an inverse, T inverse, right? And what's that inverse function going to do? Let's say that T takes the vector A to the vector B. Well, T inverse is going to take the vector B back to the vector A, right? And what's going to happen is that if you think of T composed with T inverse, so this means do T inverse first. So it means take B to A and then apply T, you're going to get B. And so what T inverse composed with T is, that's the identity mapping on Rn. Okay, I don't know what the symbol is. Let's call identity mapping on Rn. Okay, so this is the linear transformation that's represented by the identity matrix. It just doesn't do anything to any of the vectors. It just maps x to x. And we also know that if you do T first, and then do T inverse, that this is also going to be the identity on Rn. Right? Because if you take A and then apply T, you get B. T inverse will take it back to A. And so net, when you look at what you ended up doing, you just mapped A back to A. So in terms of matrices, so this is in terms of functions, right? Now in terms of matrices, what is this saying? Remember, when you think of the composition of linear maps, what does that correspond to in terms of matrices? What operation? Multiplication, right? We defined matrix multiplication in a way so that it corresponds naturally to function composition. So what equation involving matrices do I get from this first equation? This says that if I do T inverse and then do T, I get the identity. Let's call the standard matrix let's call the standard matrix of T inverse A inverse. Okay, so let's say the standard matrix of T inverse is called A inverse. A to the minus 1. In terms of matrices, this first equation says that A times A inverse is the n by n identity matrix. And the second equation tells you that A inverse times A is the identity matrix. So this is the key property of the inverse of A, that when you do A times it, you get the identity matrix. And when you do, actually in either order, you get the identity matrix. Okay. And this leads us to a following result, which I should write down. So the theorem is, if there is a matrix B such that, so I should clarify that A is an n by n matrix. such that A times B is the n by n identity matrix, or that B times A is the identity matrix, then B is the inverse of A. Okay? Do we understand what that's saying? So the hypothesis is that A is an n by n matrix. I should say let A be an n by n matrix. If there is a matrix B such that AB is identity or BA is identity, then B is the inverse of A. Maybe I should, to be more precise, it's a bit pedantic, but technically, in order to speak of the inverse, you need to know that A is invertible. So maybe it's better to say that A is invertible and B is the inverse of A. That's a more mathematically precise statement. So let's do an example. Let's say that A is this matrix, 1, 2, negative 1. That's the first row. The second row is 2, 5, negative 1. The third row is 1, 2, 0. And let's say that B is the matrix, and I'm reading off the rows. 2, negative 2, 3, negative 1, 1, negative 1, negative 1, 0, 1. Okay. So I have these two matrices, and the question says, prove that A is invertible. And find the inverse. Now the theorem says, so I have an n by n matrix, right? My n is 3. We're practicing applying the theorem. If there's a matrix B such that AB is well, in this case, n is 3, right? So the 3 by 3 identity matrix, or B times A is the identity matrix, then A is invertible and B is A inverse. Well, we're given A and B. So let's check that A times B is the 3 by 3 identity matrix. So if I take A times B, and multiply it, so if I take A and multiply by B, what do I get? Well, let's multiply. Okay, I have to do 9 computations. So if I take the first row and first column and multiply them, I get 2 minus 2 plus 1 is 1. If I take the first row and multiply by the second column, I get the 1, 2 entry that turns out to be 0. And I will also get 0 in the 1, 3 entry. And then I'm just going to skip this and just say that this is what you get. Okay. You can check on your own time to be sure, but it's really just arithmetic, right? But it's a good idea just to practice multiplying matrices to make sure that you can do this. So I get the 3 by 3 identity matrix, and therefore by the theorem, A is invertible. So I should say maybe by the theorem above. A is invertible, and B is the inverse of A. So pretty simple, right? I don't actually have to row reduce A to get the identity matrix. And also, if you row reduce A and get the identity matrix, that just tells you that A is invertible. It doesn't actually tell you what the inverse is. Okay. And maybe I probably should have stated this. A inverse is called the inverse of A. If that wasn't clear already. Okay. Let's make a comment about this theorem. So the theorem says that you just need A times B as the identity matrix or B times A as the identity matrix, not and, right? So either one will do. And the reason for this has to do with this interesting fact, which I'm just gonna state as a theorem, but I'm not gonna prove it. It's if A and B are both square matrices. I might prove this in a different video, but I don't really want to spend all the time proving this. And A times B is the n by n identity matrix, then B times A is also the identity matrix, and vice versa. So this is saying that if I have two square matrices and I multiply them in one order and I get the identity matrix, then when I swap the order and multiply them, I will still get the identity matrix. Now that's kind of surprising because in general, the order, remember, matrix multiplication doesn't commute, right? A times B is not in general going to equal B times A. Sometimes for particular A's and B's, they're the same, but oftentimes, most of the time, unless you're lucky, they're not going to be the same. And but what the theorem is saying is that if you do A, B, and you get the identity matrix, in that case, then A times B is the same as B times A. Okay. And so what that means is, so in this example, we have this matrix A and this matrix B. When you do A, B, you get the identity matrix. And if you do B times A, it turns out, if you do the math and it's correct, you will also get the identity matrix. So you really only have to check one direction. So that's really useful if you want to check if two matrices are inverses of each other. You just multiply them in one way, and if you get the identity matrix, then they're inverses of each other. And let's make one comment. We also could look at the inverse of A inverse. So I know that if I do A times A inverse, I get the identity matrix, right? So this tells me what would be the inverse of A inverse? Is there an inverse of A inverse? Well, the theorem says that if I can multiply A inverse by a matrix and get the identity, that matrix is going to be the inverse. So can you see can you see from this what that's going to be? Just give it a bit of time. Yes, it's going to be A, right? A inverse is equal to A. Okay? Let's do maybe some comments. I'll just make also another remark. What happens if you do A times B? So suppose that A and B are n by n invertible matrices. So you know that they're invertible, so they do have inverses. Then it turns out that AB is also invertible. Okay, why is this true? Can you come up with a matrix such that when you multiply, you'll get the identity matrix? It turns out that if you take B inverse times A inverse, this will work. Okay, let's check why. If I do A times B inverse A inverse, remember matrix multiplication is associative, so I can just get rid of the parentheses. Okay, it doesn't matter which order I multiply them from left to right. And I have a B times B inverse here. Now B times B inverse, By definition, that's the n by n identity matrix. So now I have A times the identity matrix times A inverse. Well, what's A times the identity matrix? That's going to be A, right? When you multiply any matrix by the identity matrix, you just get that same matrix. So I get A times A inverse, and this is equal, again by definition, to the identity matrix. So therefore, if I take this matrix AB and multiply by B inverse A inverse, I get the n by n identity matrix. And so what that means is the inverse of AB is B inverse A inverse. And similarly, the inverse of ABC, again, this is assuming that C is invertible, is C inverse B inverse A inverse, and so on. Okay. Of course, if C isn't invertible, there's no C inverse to begin with, right? So in order for this sentence to make sense, we're assuming that C is invertible. Also, I should add that another term for invertibility that's sometimes used is called singular. Sorry, non-singular. Non-singular. And a not invertible matrix is called singular. So I'll just write that down, maybe here. So not invertible. This is an n by n matrix. A non-invertible is often called singular. Let's do a practice problem. Okay, yeah, let's do this one. And then we'll call it quits for this video. Suppose that I have this matrix A that's invertible, and the A inverse is equal to 2, 3, 4, 5, where I write down the columns. The first column is 2, 3, the second column is 4, 5. Find the inverse of 2A. Well, why don't you think about it for a moment and see what you get. Okay, let's see if we can think about this. Now, I haven't told you the formula for the inverse of a 2 by 2 matrix. But let's see if we can think about this a bit more conceptually. So I'm trying to find the inverse of 2A, right? So what matrix can I multiply by 2A to get the identity matrix? In this case, the 2 by 2 identity matrix. Let's try working with A inverse. If I just have A inverse and I do 2A A inverse, I'm going to get 2 times the identity matrix. Right? 2 times A inverse is going to be 2 times the 2 by 2 identity matrix. In other words, I'm going to get this matrix. So what I need to get the identity matrix, which is this, is I need to take half of A inverse. If I take half of A inverse, 2 times A times half A inverse, I can pull out the constants. I'm going to get 2 times 1/2 times A inverse, and that's going to be 1 times the 2 by 2 identity matrix. So 2A inverse, we discovered, is equal to 1/2 A inverse. Okay, so 2A inverse, that's the thing we want, is 1/2 times A inverse, and we're given A inverse. So we just take half of each entry. That's going to give you 1, 2, 3 halves, 5 halves. So that's the answer. let's actually find a formula for the inverse of a 2 by 2 identity matrix. Sorry, not the 2 by 2 identity matrix, just a 2 by 2 matrix. So the inverse of a 2 by 2 matrix. This is a handy formula to remember. So the theorem is if A times D minus B times C is non-zero, so in other words, if I multiply these two diagonal entries and subtract the product of those diagonal entries, then this matrix, so let's call this A, then A inverse exists. In other words, A is invertible, and A inverse is 1 over AD minus BC times D negative C negative BA. Okay. So that's the theorem. So this is definitely, again, worth memorizing. Okay. So let's see why this is true. If AD minus BC is non-zero, then I can certainly take 1 over AD minus BC, right? I don't have this issue with dividing by 0. Now let's just check. So what do we need to do to check that two matrices are inverses of each other? We need to multiply them and make sure we get the identity matrix. So we need to check that this matrix times this matrix is this matrix. Well, this scalar we can pull out. So we're going to get that this times this. Let's multiply. So we get 1 over AD minus BC. And if you multiply them, you see here, if you look at the first row and first column, you get AD minus BC. If you take the first row and second column, you get A times negative B plus B times A, that's 0. If you take the second column and, the second row and the first column and multiply them, you get CD minus DC, which is also 0. And if you take the second row and the second column and multiply them, you get also AD minus BC. But I have this factor of 1 over AD minus BC here. And remember, when I take a scalar multiple of a matrix, I scale each entry, okay? And that's going to give me 1, 0, 0, 1. So I do get the 2 by 2 identity matrix, and that explains why the formula is true if AD minus BC is not equal to 0. And then there's a second part, which is, second part to the theorem is if AD minus BC is equal to 0, then A is not invertible. So it's easy to tell for a 2 by 2 matrix if it's invertible or not. Just calculate AD minus BC and see if you get 0 or not. Okay, now why is this part true? If AD minus BC is 0, then what happens is that, and I'll let you think about why this is true, but if AD minus BC is equal to 0, then there are a few possibilities. But then the echelon form of A will have a 0 row at the bottom. so you don't get the identity matrix. Okay, if AD minus BC is equal to 0, so one way to think about this is that that's the same as saying that AD is equal to BC, right? So if I have A, B here, and C, D, the thing is that you have to look at different cases. But if you have... Yeah, the thing is it's complicated because you have to look at different cases depending on if A and D and B and C are 0. But basically what happens is that CD will be a scalar multiple of AB, or AB will be a scalar multiple of CD. Right, so something like, so this has linearly dependent rows. And you can look at the different possibilities. You could have something like A and B are 0, and then you have something like this. This is going to row reduce to this. If A is not 0, then let's see. See, what I want to say is that C over A is equal to D over B. But that's if A and B are not 0. Right? If C over A is equal to D over B, then basically this second row is a scalar multiple of the first row. But you could have that the first row is a scalar multiple of the second row if one of the rows is 0, and so there's different cases to look at, but basically what's going to happen is you're going to get something like this. Okay, this is also going to row reduce to a matrix with a 0 row, and you'll see that the matrix cannot be the identity matrix. So another example might be something like 2, 3, 4, 6, right? This case, AD minus BC is 0, and you see that the second row is just a scalar multiple of the first row. And this matrix will reduce to a matrix with a 0 row. All right, so that's 2x2 invertible matrices. How to tell if a matrix is invertible or not. And in the next video, we'll talk about how to calculate the inverse of a matrix. Okay, thanks for watching.